and we will soon be taking questions as well. But first, Anders will present the program. The questions will be asked by you on the Q&A section. You should please state your questions clearly with as much detail as possible and only once. Thank you. You can use the comments part on the questions to be able to raise questions. All of you are able to see each other's questions. So if you want to add context to your question, or you want to add more information from somebody else to a question, you are more than free to do so. Please note that we have a program director here. We will not be wasting his time with questions regarding documentation or irrelevant questions that are, or questions that are not relevant to the program itself. So please keep your questions relevant to the subject matter of the day. And please feel free to contact us. At the end of the presentation, there will be a couple of slides which show you the ways in which you can contact us. So please feel free to take a screenshot, or as I said, this webinar is being recorded, which means that it will get uploaded onto YouTube, our YouTube channel, and also on Youku for China. So without further ado, I would like to introduce to you Anders Hellman. Anders, you can please turn on your camera, microphone, and please take it away.
Thank you very much, Avil. Thank you for that introduction, and welcome everyone to this webinar. I will present this master program on physics that we have at Chalmers. But first, I will just have this quote that is sort of formulating what we want to teach in the master program. So it's really solving the unknown unknowns of tomorrow. So in the world today, there are many things that is going on: technological developments, crises concerning environment and energy and so forth. And we believe strongly that a basic foundation in physics is key when we are facing these problems ahead. So as I will mention, I'm Anders Hellman. I'm the director of this master program, and I will try to guide you through the setup and the curriculum of that program. So please, could we go to next slide? So in the master program of physics, we try to focus on not only bringing basic physics to you, but also providing you with all the problem-solving techniques and skills that you need to both work in industry and in research. We also have the international and national perspective in our program. So a lot of the professors that are teaching you are international professors or coming from abroad. And it also gives that broader perspective. We have also a number of international students, of course, so it's a variety in the student body. So from the perspective of physics, we would like to build our knowledge from three legs, so to speak. So it's one, the theoretical foundation, really how theory and models help us to understand the world. But we also need to have experimental techniques so we can ask these questions to nature. So we have state-of-the-art experimental setups at Chalmers. Third leg is, of course, the computational leg or approach, which today is maybe very fruitful in that respect, that a lot of the computers are strong and you can ask serious questions and you can solve really difficult problems with the computers. So these three different directions are integrated in the program. Once you have these toolbox, you should be able to solve a number of problems, both in industry and in society. And of course, it's driven by our basic understanding of the fundamentals. Furthermore, you will also have this, that it will give you the opportunity to look for new solutions to the problems of tomorrow. So please, Emil, in the next line. So how do we do that in the master program? As in most cases, the master program is a 2-year setup, and we have a compulsory part in the beginning where we try to give you the tools in these 3 different directions. So that's the theory with quantum mechanics, really building the fundamental of what physicists view the world. The experimental methods, and that's, you will then get a chance to get into the research groups at physics and also in the astronomy department to really see what kind of experimental tools we have at the research front. And also how to deal with the new development in computers. So that's big data, neural networks, machine learning, how to understand the world from a data perspective, but also with the touch of physics. So it's all derived from physics related problems. So after that first introduction to the three different pillars in our master programs, we will have a set of preparation courses, and you will see the names later. These courses will give you further tools to really follow the different courses and get your in-depth knowledge in some of the tracks that we have in the master program. So as you see here, you will have the introduction part, the first study period, followed by these preparation course in the second period. And then afterwards, you will have the ability to choose a variety of different courses. Now, I will present some tracks where we have tried to guide you how you should follow one of the specializations, but you have the option of actually choosing in between and going with the courses that you like. But there will be a progression that I will show you soon enough. After you have finished 1.5 years, you will then pick a master thesis topic that should be driven towards physics-related topics. So that could be research-related things like quantum mechanics or galaxies or string theory or machine learning and so forth. And it will of course be connected to the number of courses that you have previously read. So that's the basic build-up. Now I will just show you the different specialization or tracks that we have in the master program. So please, the next slide. So of the 4 different specialization tracks that we have in the master program of physics, the first one is astronomy, where of course we turn our eyes to the galaxy, to the universe as a whole. And here you will then learn how you should view how the planetary system is evolving, how galaxies are formed, and so forth. And you will also have the opportunity to go and visit Uppsala and work at Uppsala, which is the national lab for astronomy observation. Now below here, I've shown you a few figures that comes from the researchers and teachers that are involved in the master program. So of course, the one to the left is the famous picture of a black hole. So some of the researchers here at Chalmers was involved in developing that tool or these data that could build that picture. In the middle part, you also see how the stellar medium in the universe is distributed, and the telescope at Uppsala can then probe these things. The last picture is also a similar picture, but in the microwave regime. So you can view the galaxy and the universe at different wavelengths, and we specialize in those things. The next slide, please. The second track is the computational physics, which is of course a relatively new branch in physics, so really benefiting of the development in computers. So here you see that the track evolves through how you can use the computer to solve ordinary differential equations, so that's typically the computational physics, and then the partial differential equations, so that's related to electronic structure problems and the Schrödinger equation, how to solve that in different levels. But you also will see how you can make finite differences and solve Maxwell's equations, flow dynamics, and so forth. So really how to take the theory and discretize it and put it in a computer and let the computer do the heavy work. We will also have specializations in advanced machine learning, really seeing what the new techniques and algorithms can learn or help us to understand nature. But we also have a possibility to study quantum computing, which is a hot topic, and Chalmers is one of the places in the world where we are actually developing these quantum computing. So that's an opportunity to really see state-of-the-art development in that respect. I've shown you a few figures below, and the first on the left is electronic structure, how computers can help us to model how materials work from Schrödinger equation. So in this case, it's the hydrogen sensing, how to sense hydrogen, and that is of course key if one wants to develop towards a hydrogen society. In the middle, you will see the plasmon, or how the electromagnetic field is developed around a beam in this case. So, and that is of course related to how you should use fusion, for instance, how you should model Maxwell's equations under these extremely strong conditions that are in the tomahawk, for instance. On the right side, you see an application where machine learning is the thing, where we build these neural networks and train it with some big data that we can generate either from quantum mechanics or from experiments and so on, and really try to learn how nature behaves. Next slide, please. So, and then the third track is the high energy physics. And that is, of course, what one would say a theory track, where you view the world from a theory point of view, how our models and theories can break down the symmetries and approximations in nature and trying to get an overall view of how to view the world. And it of course brings to the larger picture where gravity is key. So that's general relativity, black holes, how to view those things. And since especially the Nobel Prize this year goes to the black holes and the development of how to view that, we are very glad that that prize was awarded this year. But you will also see how we take the modern techniques in quantum field theory, how to understand the world in the subatomic level. Also how we see the standard model of particle physics, and also string theory, which is sort of a candidate for the unified theory of how to describe the world. I've shown you a few pictures. So in the left, you see the Feynman description of quantum field theory. In the middle part, you see Penrose's description of black holes. So that's related to gravitation and cosmology. And then on the right, you see the Mexican hat, which symbolizes symmetry breaking at different theory levels. So that's interesting as well. And then the final track, so that's the material science. And of course, this is a big track because most of our research and what the students actually goes and to work with is of course related to material science. We are, so to speak, stuck in the periodic table. So here you could see more different courses that focus on different things, and you can, for instance, have a theory-driven perspective on material science, and then you should have statistical physics, how to understand when a lot of these particles interact with each other, and then you can see quite a number of other phenomena than for the single particle case. So statistical physics, condensed matter physics, and so forth gives you the theoretical background to handle material science. If you're more driven towards experiments, we will then look at the state-of-the-art instruments and techniques through the spectroscopy course and advanced microanalysis, imaging, surface and nanophysics. So that's really driven to more of the experimental approach, how to view these phenomena at an atomistic scale. So it's really state-of-the-art techniques. And you see that we have a range of different packages here. In the end, I show you a few flavors where material science is important. So on the left, you see the battery, which is of course key in our transformation to a fossil-free society. You also see some pictures where we have hydrogen sensing, cleaning of mercury from water. In the middle, you will see how we view living tissue, viruses, and that is of course very important now when we face COVID and the crisis associated with that. So how to deal with living materials from a physics perspective. You also see some more exotic things like excitons, so that's excitations in the band structure of different materials, but you can also see the melting of gold at room temperature, depending on strong electromagnetic fields. So there is a variety of things you can study in the material science track. Please, next slide. So once you come and enter this program, what will you actually learn and what can you become? And of course, this program is designed to prepare you for both industry, so that's a key thing. You should have an opportunity to work with state-of-the-art questions in industry. For instance, the battery industry is crying for highly educated people towards material science. Of course, you should also be able to do consulting, teaching, and of course, research in either in industry or research organizations or in academia. There is the idea is to really benefit or promote your experimental and theoretical techniques. So you should be able to have those when you problem solve different things that could be the unknowns of tomorrow. So we don't really know, but the techniques should be general enough to apply for whatever problem that you are facing within 1 year, 5 years, or 10 years. So it's really not designing you for a specific technique, but giving you that broad toolbox that you need for actually having a career for many, many years to come. So that's important. We also have a good research connection throughout the master program. So all the teachers, the departments are heavily involved in state-of-the-art research, and that is then taken care of or introduced in the various courses throughout the master program. So you should really be at the research front after you exit this master program. At Chalmers, we have a number of these advanced area of the advanced where we try to incorporate research with both the education and society and so forth. And the master program is well connected with a number of these area of advances. Please, the next slide. So here I just, because one very common question is what industry or what do students work with after they exit the master program? And here I put out a number of industry partners where our students actually work afterwards. So this is from an alumni study that we performed a year before. So of course, most of our students end up in these big companies where they then typically end up in the research development, where they do the development or research of the different techniques. So it could be Ericsson, devoted to more the mobile phone techniques and so forth. It could also be the car industry, and we have Volvo, I must have missed it. Volvo and other companies. We also have space directed companies like Rogue and aerospace and so forth. And many of our students end up in these companies. You also have AstraZeneca, which is one part where students end up. So these big companies, of course, is the main employees of our students. But the students also actually have a track record of being involved in these new startup companies. And I've shown you 3 startup companies where physicists work or have been part of the development. So that could be Antium, which is cleaning of water from mercury, exploring using plasmonics to have sensors or probing the state of batteries and so forth. Revibe, where you collect the vibrations from phonons, so that's the vibrations, and you can then collect those. And those are technologies that are state of the art and really requires people that are specialized in physics at this high level. So please, the next slide. So another employee is, of course, the research institute. So that could be CERN, RISE, Fraunhofer, and Swedish Environmental Institute, which hires physicists because they are so well trained in the state-of-the-art techniques. Some of our students, of course, go on and become PhD students. And here I've shown you where some of our students has ended up at the different universities. Of course, Chalmers and Göteborg's universities are main employees in that respect, but we also have people going to KTH and Uppsala, or even going abroad. So in this case, it's students that ended up in Leiden and also in Stanford University, really showing that we give this international perspective and have a good reputation throughout the world. I think that are most of the slides that are connected to the master program. So I really, if you want to take over, or
yeah, it's there's nothing much more for me to say other than come to the very boring part of saying that there are a few important links that you can visit. Of course, this is chalmers.se/masters for all the master's programs, and one of them is, of course, physics. We've got the /tuition fees link for the tuition fees, and those of you that are wondering about scholarships can go to the scholarships page. And there are a number of other webinars that we are organizing. For example, tomorrow we will be having a walkthrough with our applications. And in fact, on Thursday, we will be meeting the admissions unit. So feel free to visit this page, chalmers.se/meet us, and register for our webinars. And then you will be able to meet us on other activities as well. And that brings me to the last two ways in which you can contact us. You can either scan this QR code, take a screenshot, save it, or even watch the recording that will be uploaded later on. Or you can visit bit.ly/chat with Chalmers students, where all the words are capitalized at the beginning. And this is a page where you can actually chat with our students who are currently studying the different programs. In fact, there is a student who's studying physics, I think, who is on this platform, and you can communicate with him. He's bound to be able to give you a few good pointers as to what the content of the program is like, and the experience of studying such a program from an international perspective. We also ourselves actually are available on this particular page. So you can actually chat with me and my two other colleagues who are on this chat at the moment. And we will be able to answer your questions as well. Anders, however, is not available on this platform. We have some other channels through which you can contact us. We have our email address, our YouTube channel, our Instagram channel, blogs, Facebook. Those of you that are in China, we've got Weibo and WeChat, so you can join those channels. We also have a group on WeChat, so please feel free to find us. For those of you in Indonesia and Thailand, we've got Line and Telegram for Iran, and WhatsApp for Nigeria, Brazil, and Uganda. So please feel free to join us at any point in time. And now we will actually go on to the questions. So why don't we actually start the share? And we've got the two of us on camera, and we can start answering questions. So I'm going to start with the first question, Anders. Actually, so here is something that all of you can actually think about. You do not have to refer to anybody at Chalmers with honorifics. So no sir, no mister, no professor, none of that stuff. You can just call us by our first names. It's Abi and Anders. That's it. Right. So because the question is actually phrased, "Hi, Mr. Hellman." That's very unusual for Anders, I'm fairly certain. With that said, the question goes like this. Could you introduce the current development of quantum computing research in Sweden and the role of Chalmers University and Department of Physics plays in it?
Yeah, so of course I should refer to the quantum computing group at Chalmers. So that is a group that contains both experiments and theory. So that's quite a big group. They have a quantum computing device that, I should of course not promise anything, but there is a number of qubits. I actually don't know the actual number, but they have a quantum computing device that has a few qubits, and they can then perform these things, testing the device. It's a big supported research program from one of Sweden's big private financiers. So that's Knut and Allison, that have given a lot of money to Chalmers and to this research group, and to really push our understanding of the quantum computing devices. Of course, one should one should of course have some respect to Google and so forth, which are of course sort of a different level. But given a sort of an international level, Chalmers then of course these groups have a very good reputation. So and I could probably share that link to these computer groups, so you can see the state of the art. So please don't hesitate to write me explicitly, and then I can give you the links, and you can have a look at how the development is going. But of course, since it's not my research field per se, I'm not so involved in actually state that they are in. So sorry for that. Yeah.
No, but Anders, actually, it could also be possible for us to actually navigate the website right now to kind of show them what parts of the website refer to such activities. Would you like to guide me while I do that?
Yes, please. So I think if you go to MC2, so that's the research.
Okay, so we click on research on the top.
Yes. And then you should find the different departments. Yes.
Departments are
Here.
here.
Yeah. And then, yeah, exactly. And then this is that's the micro
Technology and
technology and knowledge.
nanoscience.
Yes.
Okay, we click on that.
And then I see that, so you have a carousel there, and I think the fourth person in that carousel, that's the one. Yeah, so that's Per Delsing, and he's the head of that quantum computing effort that we have in Chalmers. And
Right.
it would be nice if that could sort of lead to that part. So yeah,
Let's
research
see. Let us
projects
see.
should be.
Otherwise, I think maybe on the side with the laboratories, we might be able to bring it up. But Paradel Singh, okay, article, we've scrolled down. Oh, that's a long article. Okay. Light in a
Yeah,
vacuum.
so that's so if you see there, if you go up again, or so read a recent teacher. So that's the quantum. So that's related to quantum computing, and of course, so I should not.
But this is an external page, right?
Yes, so that's the private financiers, and
Ah,
of course they are promoting the research, obviously. Um, but it's extremely interesting, and of course he's also looking at how phonons can interact with light and so forth. So his research topics is highly interesting by its own. Um, yeah, I'm a bit.
Quantum technology, quantum device physics,
Hmm?
and quantum physics. But
Yes, so I
yeah,
think
in any case, I believe, I think we've come quite far in helping people find out. So you that asked the question could also simply take yourself to the micro technology and nanoscience department page and then surf around. You will most definitely find your way to the quantum computing section.
yes.
Cool. So we will stop the share. We'll come back to you, and it's time for the next question. And the next question is there any general relativity or numerical relativity related research in those tracks that you have in the program?
Oh, so let's see. Could you?
I can bring up the presentation. And we will go to
And
this
could you repeat the
slide.
question, please?
Yes, absolutely. Just give me a second. So this was the track. No,
Yeah.
this was the track.
Yeah. So that yeah, exactly. This is where quantum computing is sort of one of the course that you can take from that track.
Hmm. And there was one where the question is there any general relativity or numerical relativity related research in these tracks?
Maybe I'm misunderstanding the question. Sorry.
But maybe we can ask for context. So you that have asked, Lin, can you, Jongji Lin, I'm sorry, I'm massacring your name, please forgive me. It would be useful if you could add a comment to your question to be able to give us the opportunity to answer it better than we are able to at the moment, yeah? Yes. But we'll go to the next question while the person gives us the context necessary. So we've got this one. It's the same person asking one feedback. The Wallenberry quantum computing thing is not listed or mentioned in the website of the Department of Physics. I found it by Google.
Yeah, exactly. So one should, of course, so the master program of physics is, of course, the education master program, and it's not. Although many of the courses and many of the involved people come from the Department of Physics, we also have courses and professors from the Department of Space, Earth and Environment. So that's a different department. And we also have teachers and professors from the MC2, that's the microtechnology department. So at Chalmers, we have a few departments that contains physics-driven education and research. So although the quantum computing is actually at a different department than the Department of Physics, you can still have the courses or the education that is in the master program of physics. So that is sort of a technical issue from the research and the educational part, which is two separate things at Chalmers.
Right. So just to also maybe clarify it further, research is more departmental, education is interdepartmental. While
Yes.
research can also be interdisciplinary, there is no questioning such a fact. But the education is definitely interdisciplinary and will take its strengths from different departments in order to complete the education that a student will go.
Yeah, exactly. I mean, the key thing is that the student should have the best teachers and have the best curriculum, so they really get to the state of the art. So that's the focus. And then the department where the researchers and professors belong is not an issue from the educational system.
Exactly. The next question here is, yes, we've got some more honorifics. Congratulations. Today's your day, Anders. Hello, sir. This is Shalik from India, currently pursuing bachelor's in physics, third year. My doubt is about credit requirements here in India. We have different credit system for masters in Chalmers. I'm sorry, Mohammed. Your question is not really related to the program. It's more related to your eligibility. And I would recommend that you then raise this question to the admissions office, who will be the ones who will be deciding. Anders is not necessarily deciding on your admission. He might read your motivation letter, but that is as far as it goes.
Yeah, true.
Right. But Pedro Acosta asks, I know that Chalmers has an excellent performance in graphene research, in both theoretical and experimental projects. I would like to know what are skills I need to have to successfully enroll in one of those experimental projects. Is it mandatory to have experience in techniques such as CVD?
No, so of course, if you come to Chalmers and then enter the master program of physics, there is actually a number of the courses where you will come into the labs where graphene is then developed and tested and so forth. So during your master program experience here, you will have the opportunity to actually get inside the labs and also then test and be part of the research teams. But so I'm not sure that I wouldn't say that there is a request from the master program that you need to have some experimental tools. You will have the opportunity to learn these tools once you're in the master program, so to speak. And of course, since the idea is that we will provide you with the state-of-the-art knowledge of these highly exciting materials. So that's graphene is, of course, the two-dimensional system, which is just one atom layer thick, right? So, but there are a number of these 2D materials, and we actually have a competence center at Chalmers focusing on these 2D materials. And of course, we have the graphene flagship from EU. So a number of researchers and professors are involved in that. And of course, since they are in fact teachers in the courses, you will then experience that research front.
Cool. In fact, speaking of 2D materials, don't we have something that's associated with boron?
Yeah, so the fun thing with 2D materials is, of course, that there is actually quite a number of different atom combinations that generate these 2D materials, and of course graphene maybe got the most attention in the beginning, and it has certainly extremely interesting properties, but the whole family of 2D materials are important in so many ways. I mean, of course, in battery research, in fuel cell research, it's all about how much you can store. And a 2D material has that flexibility of actually storing a huge amount of energy. So it's interesting from so many perspectives. It could be from the theoretical point of view, these extremely exotic materials have interesting properties as such. From an experimental point of view, how challenging isn't it to actually deal with one atom layer thin materials? And then of course from an application point of view, where a huge amount of different problems might be tackled with these 2D materials. So that's interesting in itself. Yeah.
Cool. Jong actually came back with context. So
Yes,
the question regarding general relativity and numerical relativity. So the question is this: is there any general relativity or numerical general relativity research in the Department of Physics? And which track should I choose if I want to go in that direction?
Yeah, so if I stick to general relativity, which is sort of a topic that I at least have some understanding of, or at least, yeah. So then there is of course some research groups at physics that are involved in trying to for instance, figure out what dark material is, what dark matter is, and how to probe that. And that is related to how we deal with black holes. There is also some experimental groups that actually takes the techniques that one can use to calculate or numerically calculate how the black holes behave, but then use these highly mathematical techniques in solid state physics instead. So there is a number of research groups focusing on the theoretical description of what I would say then related to general relativity and black holes and all of that research. And then we have in the Space, Earth and Environment Department also experimental groups that are developing techniques of how to study these black holes. And for instance, that black hole picture is a few of the professors at that department is involved in generating that picture. A fun thing with the picture is actually that it's related to the computational track, and that is that the program language to generate that picture was actually largely developed in Python, which is the language that is used throughout the computational physics track. So it's interesting how all of these techniques interplay with each other and are important to really be at the bare front or forefront of research. As for the numerical, I will pass on that, unfortunately.
Well,
I kindly ask the student to write to me in person, and then I will try to figure out how to respond in a better way.
Exactly. So in case you're wondering how to get in touch with Anders, you would go ahead. And so this is the page for the program, right? So I started at education. I clicked on master's studies, the master's programs, and then I chose physics. And this is the physics page. And over here, you would have, oh, by the way, this link would get replaced with a recording of the webinar. So you'd be able to watch it, I'm assuming, at some point in time. But in any case, you have his email address right here. And you can just click on it and say, hey, Andish, I have a question. And this is what I'm wondering about, right? As long as it's not about how many credits do I need to have, right? Please don't ask him that question because he can't really answer that question for you. That's an admissions related question. Right. And I was actually about to show you something else over here as well. Under here, we actually have a link to the department, if I remember correctly. Yeah. So here are the different departments that the program actually draws its courses from. This list is not always thorough or complete or exhaustive, but it does give you an idea as to which departments the program draws its courses from. So you would be able to see that obviously the microtechnology and nano science department
should be there. Yeah.
But it does draw its strengths from different areas. It is mentioned over here, however. Yeah.
Yes.
So. Cool. So we stop the share once again. We go back to our questions. Anders, let us see. What do we have here? Ivan is asking, hello, I would like to ask if the research thesis in the second year is always just one term, or is it offered for two terms? That is all of the second year as well. Also, is it possible to do this thesis at an external institute in Europe, say CERN or IRAM or Max Planck, etc., if we reach out to them and they are interested?
Yes, correct. So the curriculum I showed, then it was only the 30 credit point master thesis. But at Chalmers, we have the option of having a 60 credit master thesis work. It's then typically divided with, so you have a half-time seminar showing your progress and so forth. And that I can recommend if you really want to pursue a research career and you sort of know at which topic or track you're interested in, then the 60 credit point is, of course, a very, very nice option where you can really focus on the research topic that you're interested in. So yes, on the first question. Then on the second question, yes, again, yeah. So the only requirement for doing a master thesis project here is that the examiner has an association to Chalmers. So the examiner needs to be here, but the project and the supervisors can of course be an external institute like CERN. And this is quite, it's not uncommon that our students go abroad at different departments and institutes and so forth and do the research. So CERN is of course one where we actually have students performing that. So we have some experience of how to do it. So yes, on both accounts. So that should be okay.
Excellent. Yes. Let us see. Yes, we have one more question. One important question: how the COVID situation will affect teaching in 2021? Time to play Oracle now, Anders.
Yeah. So of course that is. I think there are some famous quotes that it's very hard to make predictions, especially about the future. So of course, COVID is hitting the education system quite hard. I mean, it's distance and so forth. But as in most cases and in most places in the world, we are placing a lot of hope in the vaccines, and they will progress in the spring. So hopefully we will break that general pandemic throughout the spring terms, and then we will have the possibility of returning to sort of normal education. Of course, during spring, if we just project what we know from now and the situation we have as of now, then most of the lectures and so forth, that will be still at a distance, so via Zooms and play recordings and so forth. Whereas all the experimental work that we do, we actually invite the students to Chalmers, to campus, to really perform these things, because of course in that case the hands-on experience is so key in learning how it's done. So we are trying to have a mixed how we educate the different courses. So if there are experimental driven, you will have campus-based education here. But in most cases, it's of course lectures and so forth at a distance. So, and as far as I know, this is what we plan for during the spring. Sorry to say.
Yeah, exactly. But the thing is also like, so for these students that are talking to us on this, right, they're actually planning on starting in the fall next year.
Yes.
And
Yeah.
that is 9 to 12 months away. It's not
Yes.
something that we can, or 9 months away. It's not really possible for us to predict something at that distance in time. But also we must kind of go back to the our DNA. We are an on-campus university. That's what we
Yes.
are.
Yeah.
and
Absolutely.
and as soon as we can go back to that, we will go back to that. So
Yeah.
meanwhile, we're going to be doing everything we can to kind of create this blended system where we have online lectures or offline lectures when and where necessary, but definitely all the experimental parts, as you mentioned, all the laboratory moments are physically carried out
Mm.
with all the restrictions and all the recommendations taken into consideration. So it's not that we're flouting the rules here. It's
No,
definitely
no,
that we are.
it's a lot of security around it. So the students should be safe
Exactly.
in that way.
Yeah.
But I agree. I mean, of course, for students that are looking for entering the master program in the autumn, we are definitely hoping that the situation has then become under control, and then we will go back to the on-campus teaching.
And we are also actually to kind of speak of something that is slightly allied to this, and that would be that are we expecting students to be on campus? And there I think the answer is quite a strong yes. We don't have any written information about this, but I believe that will also be a part of Swedish migration agencies requirements and things like that. And I think we will have to require that our students are present on campus and in on location, even if they can't necessarily take classes physically. They will still be required to attend in person, as in on location.
True.
Yeah. Anyway, moving on, we have Alicia asking us, hello, I'd like a bit more information about how different tracks are expected to mesh with each other, since the master's outline recommends picking out 2 tracks. For example, if I were to be interested in a computational physics track and a high energy physics track, would I need to pick a specific number of electives from each branch to fulfill both tracks?
So that's a good question. And if you could bring up the
I'll throw up the
presentation
slides.
again, please. Um, so we have these four different tracks that and some are very connected that you progress inside the track. So if we, for instance, go to the high energy, so that's 2 slides down. So this one. So here the progression is very strong. So that means that to really understand the later courses, you should actually have taken the earlier courses. So you can't, if you go into this track, you should actually try to follow the track as close as possible, because they build on each other. And that is true if you go one up, also in the computational physics track. So Alicia has really picked 2 where the progression is very strong, which means that you should try to follow the track. But you also see that typically you take 2 courses per study period. So if you follow these 2 tracks, you immediately see that you will actually need to pick some courses, and you can't take everything, so to speak, because in the computational physics part there is 2 courses in each study period in the second year, and that you can't combine. Then you can't pick 3 courses, or we don't recommend it, at least, because it's very, very difficult. These are high level courses. So here you should then try to follow the high energy track. So there you can take all the courses, so to speak. So there the course packages are quite clear. And then in the computational track, you can then follow in the earlier study period 1, 2, 3, and 4 in the first year. And then for the second year, you should then pick what kind of direction you want to have. If it's more application driven, then maybe you should look at the plasma physics with applications and the advanced simulation machine learning, because there you learn applications more. But if you're really interested in the hardware and understanding how computers work, then the high performance computing in connection with quantum computing would give you an edge in that field. If you go to the astronomy, here the sort of the progression is not that strong. So here you could actually come from another track and then pick one of these courses in the later study periods. So here the courses are not that strongly connected with each other, and the progression should be something you can catch up on. If you go down to the material tracks, which is the last one, here progression is not that severe at all. So here you can actually take different courses that is driven by your interest. But you also see that there is quite a number of different courses. So if you follow the materials track, it's enough to follow that track, and you can completely fill all the course requirements for your thesis or your diploma from the Master of Program in Physics. So it depends really on which track you choose. In astronomy, computational, and high energy, you need to have a complementary track to fulfill the requirements for the diploma. But if you pick the material science track, you will have enough courses to fulfill that requirement. Hopefully that was some answer. It should also be mentioned that, of course, you could, for instance, if you go to the high energy, so that's this one, you could actually pick 4 completely different courses that are not in the master program of physics and still fulfill the requirements of your diploma. And that means that you could take, for instance, the high energy physics track and then complement with some abstract mathematical courses if you really are driven towards mathematical physics. So that could be another combination. You could, of course, pick something completely different, like art, science, or history, or philosophy.
Entrepreneurship.
Yeah, so that's so you will always have that possibility of picking at least 4 completely free courses for still fulfilling the requirements of your diploma. Hopefully that was an answer.
Right. I want to actually take everybody back to this slide here
Yes.
to kind of also clarify this thing. You early on in your presentation, you mentioned something called a period. Now, I'm not sure whether everybody here is aware of what a period actually means in an academic year for Chalmers. So what students need to understand is, as you can see, a year is definitely divided, as in we have 2 years, and a year is definitely divided into the autumn term and the spring term, as Ivan actually pointed out. But within a term, the term is divided into 2 once again. So we do not follow a semester system. We follow what is a quarter system. And each quarter is in turn therefore called a period. So within a period, we recommend that you pick 2 courses at a time. Now, if you picked 12 courses and then you did a 30 credit thesis, you would graduate, right? Or you would pick 8 courses and then you would do a 1-year thesis and you would graduate one way or another. Each course would be 7.5 credits, and a total of 2 years would give you 120 credits. Now, what is important to also remember here is that you, as Anders quite rightly just now pointed out, there are some courses, and also you that asked, Alicia, there are some courses that you have to take, and then there are some courses that you can pick from anywhere you want. So the flexibility exists. For example, you could pick courses from engineering, mathematics, and computational sciences, which actually has a very strongly mathematical physics kind of track in there, in addition to a whole other bunch of tracks. They have, I think, the most number of tracks, if they don't beat biomedical engineering.
Yeah.
So I mean, it's not a competition, but there's a large number of tracks there. So you could pick courses from other programs to complement what exactly it is that you want to achieve with an education at Chalmers, right? So we will stop the share here once again. And there are no questions at the moment, Andish, but I have a few for you anyway, because we know that a few students sometimes wonder about these kinds of things. How big is your program? Is it a large program? Is it a small program? Do you have a lot of contact with teachers? Or is it like I'm sitting in a classroom of 280 and I barely know the name of my teacher? What's the situation?
Yeah, so that's a good question. So normally we have like around 60 students in each year, so to speak, and of course so 60 students, that's enough to be a large program, but still you have the possibility of actually interacting with the teachers, and that is absolutely true once you go into the different tracks, because of course 60 students divided on 4 tracks, you have like around 20 students per course, around that number, and then of course it's more close to the professors that are teaching, so you should definitely be possibilities to talk with them and have a sort of a social interaction with the professors, and of course as the sort of you progress, you will the courses becomes more and more specialized. So then the number of students in each course becomes less. So really in the second year, where we have a lot of these complementary courses, the number of students might be around 10. And then of course it's a close connection during the teaching periods.
Right.
Yeah.
Here's
So
another question actually
yeah,
I'm wondering
yeah, please.
about. It's and we are actually coming to the close of the webinar, so that's it's actually good that this kind of question is coming up towards the end. Um, does your program, so what is the typical thing that a student does? Do you see a trend, or how do we put this? It's not exactly a trend so much as it's a common thing to happen in the program, that students that finish normally go into research and not so much into industry, or is it the other way around, or is it 50-50?
Yeah. So that's a good point, because I would say that the most common view of a master program of physics is they all become researchers, but that is not true. So we have a track record of around 60% of our students go into industry. So that's really either the big companies where they go into the research development, and then typically they progress to manager in some few years later, or they are involved in these really spin-off state-of-the-art companies where you have 10 employees and so forth.
Right.
But 60% of our students go to industry, so that's the private sector, and then around 5 to 10% go into research institute. So that's not really academia, but you go into research institute, and RISE is of course one big employee in Sweden. And then around 35 to 30% goes into pursuing an academic career and becoming PhD students. And of course, most end up at Chalmers and Göteborgs University because of the connection. But as I showed you in the presentation, a few of them have also pursued a PhD at international universities. But it's good that you asked this question, because it's so common that the idea is that everyone goes in there, they want to become an Einstein, and then you should pursue an academic research. But that is not the outcome from the master program. And that is, of course, key when we develop this master program, because it's quite new with respect to other master programs. Then the key thing was to actually meet up industry's requirements and really providing the tools that are needed for this highly technology future that we are facing. So that's good if the students actually feel that you don't need to become a professor in the end of this program. So
But if
that's
you
a
want
good
to,
thing.
you can, right? So here is a follow-up to that. So let's assume that a student is graduating and has the choice of both, right? They have the choice of going into industry and the choice of going into research. What would they do normally to actually start that process? Like, would they write to you? Is that how they would start with a PhD, or is that like is it through the master's thesis, that the person that they were doing their thesis with, is that the person they contact, or do they do they write to somebody at a company and say, hey, I have a master's in physics? Do you have any tips on that?
Yeah, yeah. So that's also a very relevant question. So I think from the alumni studies that we have done, then the main connection to whatever the first employment is through the master thesis. So that is a very common entry to the working life. So if you want to pursue an academic career, then you should try to pick a master thesis that is either distributed through the professors or from the departments, and that will give you a connection to whatever topic. And I should of course point out this: you should pick that topic that you like and really burn for, because that's what you will do for a number of years if you become a PhD student. But the same thing goes with if you want to go into industry. We have a number of master theses that are announced at the Department of Physics that are related to research in industry. And of course, many of our professors are having these connections to companies because we are doing applied physics also, right? So in batteries and so forth, the researchers and professors are really connected to the companies. And then that is a portal to your first employee. But I wouldn't stress it too much, because it's sometimes the focus comes that, oh, now I need to pick the best master thesis project ever to become. But it's sort of a natural thing. If you pick a topic that you like and you're driven towards, then you will get the connections to either the industry that you're interested in or to the universities and academic career that you're interested in. So I wouldn't worry too much, but the master thesis is the first portal to your first employment. So that's
right. So, and one thing that I would actually kind of extract from what you said is also the fact that the program is not just theoretical, it's not just applied, it is both. And it is you that decide, you, the student, who is deciding which part or which combination of these two you will come out with.
Yeah, exactly. I think that is the key thing, right? There are so many. Although physics sounds so narrow, there is a huge different topics and flavors that you can study in physics, and it should really be your driving and your interest that makes your education in that way. And as I said in the beginning, today modern physics builds on these three pillars, that you're having the theory, making the models and theories of how the world should be, but we also need to have these experimental tools and really investigate how nature behaves, because it's not an opinion. Nature is something that has certain rules, and we are, as physicists, are trying to figure out how these rules work, either through theory, experiment, or today then a lot of these computational methods where we solve the theory equations, the Schrödinger equation, for instance, and really try to understand how nature behaves. So I agree, there are a lot of different flavors, and the students should really pursue the topic that they are interested in. I think that is key.
Right. So that basically brings us to the end of today's webinar. Thank you very much, Anders, for a wonderful conversation and presentation.
Thank you very much, Abil. This was very interesting.
Yeah, and we had a few people that have been hanging out with us throughout this time. Thank you, everyone, for spending your time with us. I hope that the questions that we answered were useful for you. And as I said, this is being recorded, so it's going to go up on YouTube and on Youku. So please just go and visit us tomorrow, right? It's going to take some time for Zoom to encode this and download it, and then I will be able to upload it. It's going to take some time. So check it out tomorrow. And meanwhile, I wish you all safety and health. This was Chalmers University of Technology. Bye-bye.